All right, welcome back everyone to the deep dive. If you're joining us as a new intern, or maybe you're just starting your PGY 1 year, you've already climbed a pretty steep hill with chapters 1 through 6.
Oh yeah, definitely. We covered a lot of ground basic neurotransmission receptors, how these systems can, well, go wrong in mental illness.
That's the essential foundation.
Yeah.
Right. Understanding the building blocks before we start putting things together. Brain overload, maybe.
It can feel like it. But think of it like this. You've learned the key players, dopamine, serotonin, GABA, all that. You know their basic moves.
Exactly. And now we're diving into chapter 7. This is where it gets really practical. Drug treatments for mood disorders. If you're going into psychiatry, this stuff is, well, it's core.
Absolutely essential. It's a dense chapter, no doubt about it. Lots of drugs, lots of mechanisms.
But we're going to break it down for you. Focus on what you really need to know for clinical practice. We'll hit the key concepts, define any new terms we bump into, make it digestible.
Yeah, less textbook, more conversation. And speaking of getting practical, let's start with a statistic from the chapter, figures 7 to 4, that really kind of sets the scene.
Oh, this one, yeah, it's pretty sobering. Get this. Only about 1/3 of patients with unipolar depression actually achieve remission with the first antidepressant they try.
1 in 3. That really tells you something, doesn't it? It highlights why just knowing brand names isn't enough. We need to understand how these meds work and why one might work when another doesn't.
It shows treatment isn't always straightforward. It often takes persistence, careful choices, maybe some trial and error based on good understanding.
Precisely. It's about knowing the tools in our toolbox. So let's start opening that box. First up, the SSRIs, selective serotonin reuptake inhibitors, the workhorses.
Right. We know serotonin transporters, SERTs, kind of vacuum up serotonin from the synapse. Figures 716 through 721 show this pretty clearly. SSRIs basically block that vacuum.
Yep, they inhibit SERT. So more serotonin hangs around in the synapse, boosting its signal. That's the main idea. Over time, this is thought to lead to downstream changes that help lift depression.
But here's a really key point the chapter hammers home. This idea that all SSRIs are basically the same, it's just not true.
Not at all. That's a common misconception. While they all share that primary SERT blocking action, they have other secondary pharmacological effects that can be quite different.
It's like saying all cars are the same because they have 4 wheels and an engine. The details matter.
Exactly. And these details, these secondary actions, can really influence things like side effects or even how well the drug works for a particular person.
Okay, let's get specific. Fluoxetine Prozac. The chapter mentions it has some weak norepinephrine reuptake inhibition, especially at higher doses.
Right, a little bit of net inhibition, and then there's its half-life. It's really long.
Which can be good and bad, right? Good because maybe less withdrawal if you miss a dose.
Potentially, yes. Fewer discontinuation symptoms. That long tail can smooth things out.
But bad if someone has side effects or you need to switch meds quickly. It hangs around for ages.
That's the downside. Clearance takes a while, so you need to factor that in.
Okay. Then there's fluvoxamine. This one acts on sigma-1 receptors. That's a new one for us, I think. What are sigma-1 receptors?
Good question. Sigma-1 receptors are interesting. They're located inside the cell on the endoplasmic reticulum, and they're involved in modulating various cellular processes like calcium signaling and neuronal plasticity. They're kind of intracellular helpers.
Okay, so not your typical surface receptor. And fluvoxamine interacts with these.
It does. It's an agonist at sigma-1 receptors. This action is thought to contribute to its anxiolytic effects, and there's some suggestion it might be particularly helpful in psychotic depression. So it's another differentiating factor.
Interesting. A possible niche there. What about citalopram and encitalopram, Celexa and Lexapro? The chapter talks about RNS and enantiomers. Sounds complicated.
A little bit of chemistry flashback. Citalopram is a racemic mixture of 2 mirror image molecules, R-citalopram and S-citalopram. Escitalopram is just the S form, purified.
Okay, so one is a mix, one is just half of the mix. Why does that matter?
Well, the S enantiomer is the one primarily responsible for blocking SERT. But here's the twist. Some evidence suggests the R enantiomer might actually interfere slightly with the S enantiomer's binding to SERT.
Get out. So the other half might actually hinder the useful half.
Potentially, yeah. It's like it gets in the way a little. And the R form also has very weak antihistaminic properties, H1 blockade.
So maybe a tiny bit more potential for drowsiness, though probably not much clinically.
Probably not significant sedation on its own, but it's another subtle difference in its profile.
And paroxetine and sertraline Paxil and Zoloft. The chapter mentions they have other binding properties too, that doesn't go deep here, just acknowledging they're not only SERT blockers.
Exactly. Paroxetine, for instance, has some anticholinergic activity, which can contribute to side effects like dry mouth or constipation. Sertraline has a bit of dopamine transporter, DAT inhibition, though much weaker than its SERT action. These things add to their individuality.
Okay, the all SSRIs are the same myth is definitely busted. Now, Vlazidone Vibride, this is called a Asparavi, serotonin partial agonist reuptake inhibitor.
Right, so it's doing two things. It blocks SERT like the others.
Standard SSRI action.
But it's also a partial agonist at the 5-HT1A receptor. We touched on partial agonists before.
Yeah, like a dimmer switch. Not fully on, not fully off. It activates the receptor, but only partially, even at high concentrations.
Perfect analogy. So vilazodone gives that 5-HT1A receptor a partial nudge. This is thought to contribute to its antidepressant effect, potentially synergizing with the SERT blockade, and maybe potentially leading to less sexual dysfunction or weight gain compared to some agents that are purely SERT blockers. Figure 722 shows this dual action.
Less sexual dysfunction and weight gain? Those are big potential advantages, as those are common reasons people stop taking SSRIs.
They certainly can be. So this dual mechanism is trying to enhance efficacy and maybe improve tolerability in those areas.
So the big picture with SSRIs, they all hit SERT, but their side gigs at other receptors mean you really need to think individually. Empiric trials, trying a different one if the first doesn't work or causes problems, makes a lot of sense.
Absolutely. It's about finding the best fit for that specific patient's neurochemistry and symptom profile.
Okay, let's shift gears. Serotonin norepinephrine reuptake inhibitors, SNRIs, the name says it. They block both SERT and the norepinephrine transporter, NET. Figures 728 through 32 lay this out.
Right. So now we're hitting two major monoamine systems involved in mood regulation.
The idea being maybe a broader impact, covering more bases, potentially addressing more symptoms.
That's the rationale. By boosting both serotonin and norepinephrine, you might engage a wider range of circuits, potentially offering advantages over just targeting serotonin alone. Think back to Chapter 6. Different symptoms might relate to different neurotransmitter deficits.
No, and the chapter highlights some specific situations where SNRIs might have an edge, like painful physical symptoms that often come with depression.
Yes, that's become a really key area. Even though it's not in the formal DSM criteria for depression, we know many patients experience aches, pains, fatigue. Figures 7 to 5 touch on this. SNRIs, particularly ones like duloxetine, seem better at addressing these symptoms.
Why is that? The norepinephrine part.
Likely, yes. Norepinephrine pathways are heavily involved in modulating pain signals descending from the brain. So boosting NE might help dampen those pain signals. It's also why they're used for things like neuropathic pain, diabetic neuropathy, for example.
So a potential 2 for 1.
Yeah.
Treating mood and pain. That's useful. What else? Cognitive symptoms.
Yes, particularly in geriatric depression. Figure 733 points to NET inhibition in the prefrontal cortex. Norepinephrine is crucial for executive functions, attention, concentration, working memory, which often suffer in depression.
So boosting NE in that critical brain region might help sharpen thinking.
That's the hypothesis, and there's some evidence supporting it. So for patients, especially older adults where cognitive complaints are prominent, an SNRI might be a particularly good choice.
Makes sense. The chapter lists a few duloxetine, venlafaxine, desvenlafaxine, levomilnacipran. Again, different options within the class.
And again, with subtle differences in their relative potency for SERT versus NET and maybe other minor actions influencing their use.
Okay, moving on. NDRI, norepinephrine, dopamine reuptake inhibitor. Only one player here, really. Bupropion or Wellbutrin.
That's the main one. It's described as a relatively weak inhibitor of both DAT, the dopamine transporter, and NET. Figure 724 illustrates this.
Weaker than SSRIs or SNRIs at their targets.
Generally, yes, in terms of pure reuptake inhibition potency in standard assays. Interestingly, though, the chapter notes that some of its metabolites, the breakdown products, might actually be more potent inhibitors than the parent drug.
Ah, so the body modifies it into something perhaps more active.
Possibly, yeah. It adds a layer of complexity, but the key is that it brings dopamine into the picture alongside norepinephrine without directly hitting serotonin much.
Which might explain its different side effect profile. Less sexual dysfunction, maybe.
That's often cited, yes, and its activating properties for some people, and of course its use in smoking cessation.
Right. We'll cover that more in Chapter 13, but it's linked to dopamine release in the reward pathway, the nucleus accumbens.
Exactly. That dopaminergic boost is thought to help reduce nicotine cravings.
Okay, now things get even more interesting. Multimodal antidepressants. These seem designed to hit multiple targets deliberately. First up, agomelatine. Very unique mechanism.
It really is. It's an agonist at melatonin receptors, MT1 and MT2, and the sprechiasmatic nucleus, the SCN, the brain's master clock.
We talked about the SCN and circadian rhythms in depression back in Chapter 6, figures 635 and 636b. Depression often messes up sleep cycles and melatonin.
Precisely. So agomelatine directly targets that system, potentially helping to resynchronize those disrupted circadian rhythms by mimicking melatonin's action in the SCN.
Like resetting the body clock.
Yeah.
But that's not all it does, right?
No, it's also an antagonist at 5-HT2C receptors. Figure 737 shows both actions.
And blocking 5-HT2C, what does that achieve?
Blocking 5-HT2C receptors, particularly in the prefrontal cortex, tends to increase the release of both norepinephrine and dopamine. Figure 738 illustrates this effect, so you get this dual approach, resetting rhythms via melatonin agonism and boosting NE and DA via 5-HT2C antagonism.
Fascinating combo, targeting sleep and neurotransmitters. Okay, next, multimodal. Mirtazapine, Remeron. This one looks like it does a lot.
Oh, mirtazapine has its fingers in many pies. It's an alpha-2 antagonist, which is a key action.
Alpha-2 antagonism. That means it blocks the brakes on norepinephrine and serotonin release, right? So more NE and 5-HT get released.
Exactly. It blocks the presynaptic autoreceptors, but then it's also a very potent antagonist at histamine H1 receptors.
H1 blockade. That means sedation and weight gain often. We saw that link in Chapter 5.
Yes, those are very common side effects, and why it's sometimes used specifically for its sedative properties at lower doses. It's also a potent 5-HT2C antagonist.
Like agomelatine, so more NE and DA release.
Correct. And it also blocks 5-HT2A and 5-HT3 receptors.
Wow. Okay, what do those do? 5-HT2A blockade.
Blocking 5-HT2A is thought to contribute to antidepressant effects, potentially by increasing dopamine in the prefrontal cortex, and it's also linked to improving sleep quality, specifically slow-wave sleep.
And 5-HT3 blockade.
That's often associated with reduced nausea and vomiting. Some antipsychotics block 5-HT3 too. There's also some thought it might contribute to procognitive effects, similar to vortioxetine, which also blocks 5-HT3.
So mirtazapine is really hitting multiple systems thought to be involved in depression and its associated symptoms like insomnia and potentially anxiety.
It's a broad spectrum agent, pharmacologically speaking. The chapter also notes other drugs sometimes used in depression, like certain atypical antipsychotics, brexpiprazole. Quetiapine also have that alpha-2 antagonist property.
Seems like a useful target to hit. Okay, last one in this multimodal group. Vortioxetine Trintellix. Another complex one.
Very much so. It combines SERT inhibition, the SSRI part, with actions at several other serotonin receptors. It's a 5-HT1A agonist.
Like vilazodone, but a full agonist here, not partial.
The text describes it as an agonist, often presumed full, yes. And it's an antagonist at 5-HT3, 5-HT7, and 5-HT1D receptors.
Okay, SERT block, 5-HT1A boost, and then blocking 3, 7, and 1D. What's the payoff for all that complexity?
A major focus with vortioxetine has been its potential pro-cognitive effects. Figure 740 links these multiple receptor actions to improvements in cognitive function, often impaired in depression.
Pro-cognitive, that's huge because thinking problems are so common and debilitating, not just in depression, but other disorders too.
Exactly. It's a significant unmet need. The various serotonin receptor interactions are thought to work together to enhance neurotransmission in ways that specifically benefit cognition.
The 5-HT7 antagonism seems particularly interesting. Figure 753C shows it working on GABA interneurons, leading to more serotonin release. How does that work?
Right. It blocks 5-HT7 receptors located on inhibitory GABA interneurons in the Raphe nucleus, where serotonin cell bodies live. By inhibiting the inhibitor, you essentially take the brakes off serotonin release, particularly enhancing its release downstream in areas like the prefrontal cortex.
Wow, that's intricate. Like a double negative leading to a positive effect on serotonin.
It's a sophisticated way to modulate the system. It really shows how far we've come from just simple reuptake inhibition.
Definitely. Okay, so beyond these main classes, the chapter mentions other strategies, like adding serotonin dopamine blocking agents, atypical antipsychotics for depression that doesn't respond well.
Yes, adjunctive therapy. Using low doses of drugs like aripiprazole, quetiapine, brexpiprazole, olanzapine in combination with fluoxetine is an evidence-based strategy for treatment-resistant unipolar depression. They add another layer of mechanisms.
But they come with their own risks, need monitoring.
Absolutely. Metabolic side effects, movement disorders, sedation.
Yeah.
You have to weigh the risks and benefits carefully.
The chapter also cautions about predicting treatment response. Pharmacogenomics. It's not quite ready for prime time in terms of picking the right drug first try, is it?
Not really, no. It can give clues about metabolism, like who might break down a drug super fast or super slow, or maybe flag increased risk for certain side effects based on specific genes. But predicting efficacy, we're not there yet. Clinical factors are still paramount.
So combining drugs with different mechanisms like we talked about in Chapter 6 with the symptom-based approach still seems like a key strategy for difficult cases.
It often is.
Yeah.
If one mechanism isn't enough, targeting the illness from multiple angles pharmacologically can sometimes yield better results.
There's also that interesting interaction mentioned how combining alpha-1 and 5-HT2A antagonism can reduce the risk of Parkinsonian side effects from dopamine blockers. Figure 758A. We saw this with some atypicals in Chapter 5.
Right. It's a built-in protective mechanism in drugs like quetiapine, clozapine, iloperidone, and brexpiprazole. The alpha-1 and 5-HT2A blockade seems to counteract some of the motor side effects that might otherwise arise from D2 blockade in certain pathways.
Clever pharmacology. Now, briefly, the older guys.
Yeah.
Tricyclics TCAs, figure 767 shows their messy profile. Any reuptake block, some SERT block, but also hitting histamine, alpha-1, and muscarinic cholinergic receptors.
Yeah, messy is a good word pharmacologically. Effective antidepressants, no doubt, but that broad receptor blockade leads to a lot more side effects. Sedation, dizziness, dry mouth, constipation, weight gain, and the sodium channel blockade makes them dangerous in overdoses.
Which is why they're not first line anymore, generally. And MAOI's monoamine oxidase inhibitors.
They block the enzyme that breaks down serotonin, norepinephrine, and dopamine. Very effective, especially for atypical depression or treatment-resistant cases, but...
The cheese effect, the dietary restrictions.
Exactly. Need to avoid tyramine-rich foods to prevent a hypertensive crisis. Plus, lots of potential drug interactions. They require careful management and patient education.
Okay, let's circle back to some specific agents mentioned. Cariprazine, we met it in Chapter 5 for psychosis. Now approved for bipolar depression. Studied for unipolar, too. Unique profile.
Very unique. Partial agonist at D3, D2, and 5-HT1A receptors, but with a particularly high affinity or strong binding preference for D3. Also has alpha-1, alpha-2 antagonism. That D3 action is thought to be key for mood and motivation.
Interesting. And lithium, the classic mood stabilizer for bipolar disorder.
The gold standard for mania prevention, still incredibly important. Its mechanism, though, still debated after all these years.
Really? What are the leading ideas?
The chapter mentions effects on intracellular signaling cascades, things like the phosphatidylinositol system, modulating G proteins, and notably inhibiting an enzyme called GSK3 glycogen synthase kinase 3. Figure 774 touches on this.
GSK3, what's that? Sounds important.
It is. GSK3 is involved in tons of cellular processes: energy metabolism, cell survival, neuroplasticity. Lithium's inhibition of GSK3 is thought to promote neuronal resilience and plasticity, contributing to its mood-stabilizing effects.
Fascinating. And anticonvulsants are also used in bipolar, like valproic acid.
Yes, valproate is another major player, particularly for mania. Again, mechanism isn't fully pinned down. Hypotheses include blocking voltage-sensitive sodium channels, figure 776, enhancing GABA function, figure 777, and, like lithium, regulating intracellular signaling pathways, figure 778.
Seems like hitting those intracellular pathways is a common theme for mood stabilizers.
It does seem that way, suggesting mood disorders might involve fundamental problems in how brain cells signal and adapt.
The chapter briefly lists common evidence-based combos for bipolar mania and depression, often involving these mood stabilizers, plus maybe an atypical antipsychotic or sometimes an antidepressant carefully added for depression.
Right. Combination therapy is very much the norm in bipolar disorder management to cover different phases and symptom domains.
Okay, now some really cutting-edge stuff. Combination products for treatment-resistant depression.
Dextromethorphan.
Yeah, the cough syrup ingredient combined with something to slow its breakdown.
Exactly. Dextromethorphan, DXM, is an NMDA receptor antagonist. The problem is it's usually broken down very quickly by the enzyme CYP2D6. So the strategy is to combine it with a potent 2D6 inhibitor, like quinidine historically, or more recently, bupropion. Figures 784 and 785.
Bupropion. So it's doing double duty there, antidepressant and blocking DXM breakdown.
Precisely. This allows the DXM levels to rise and exert its NMDA antagonism, which seems to have rapid antidepressant effects. The DXM-bupropion combo has FDA breakthrough therapy status. There's also mention of deuterated DXM.
Deuterated, like heavy hydrogen.
Basically, yes. Swapping some hydrogen atoms for deuterium can subtly change how the drug is metabolized, potentially improving its properties. It's a drug development technique.
Wild. And then there's dextromethadone, not the usual methadone.
Right, it's the dextro enantiomer. While regular racemic methadone is primarily an opioid, dextromethadone has much less opioid activity but retains significant NMDA antagonist effects. So it's being explored specifically for depression, potentially rapid-acting too, figure 786.
NMDA antagonism seems like a really hot area for new depression treatments.
It definitely is, representing a different approach from the classic monoamine strategies.
And finally, the chapter glances at even newer frontiers. Psychedelics like MDMA and psilocybin, figures 787-88.
Yes, used in controlled settings, often combined with psychotherapy, hallucinogen-assisted psychotherapy, showing remarkable promise in early trials for PTSD and depression, potentially by altering brain connectivity and facilitating emotional processing. Still lots to learn, but very exciting.
And neuroactive steroids, targeting GABA receptors differently, figure 756b.
Right. These are steroids produced in the brain that modulate GABA receptors, but at sites different from where benzodiazepines act. Agents like brexanolone, allopregnanolone, are approved for postpartum depression, providing rapid relief potentially by restoring GABAergic tone.
Wow, okay, that was a lot. Chapter 7 is packed. But the takeaway is clear. Treating mood disorders is really complex.
It absolutely is. It requires a deep understanding of these different drug classes, their mechanisms, their potential benefits, and their risks.
And while SSRIs are often where you start, knowing about SNRIs, NDRIs, multimodals, mood stabilizers, and all these emerging options is critical. You need the whole toolbox.
Especially for patients who don't respond to first-line treatments or who have specific symptoms like pain or cognitive issues or bipolar disorder, knowing these other options is crucial.
And the research continues. The combination products, the psychedelics, neuroactive steroids. It gives a lot of hope for the future, doesn't it?
Yeah. It really does. The field is constantly evolving, searching for better, faster, and more targeted ways to help people struggling with these conditions. It's a dynamic and hopeful time to be entering the field.
So here's something to mull over as we wrap up. We've talked about serotonin, norepinephrine, dopamine, GABA, glutamate, melatonin, intricate circuits. But given this complexity, what if our current focus is still too narrow? What if future breakthroughs come from understanding completely different biological systems involved in mood? Maybe inflammation, the microbiome, or something we haven't even really considered yet.
That's a great provocative thought. It reminds us to stay curious, keep learning, and recognize that our understanding is always incomplete. There's likely much more to discover about the biology of mood.
Keeps things exciting, right? Okay, that's our deep dive into Chapter 7 for today. Thanks for joining us.